Nice to see you all. So my talk will be about reflection principles and small ultrafilter number. I got interested in this topic because I was invited to talk in Amsterdam when the workshop was on the generalized cardinal invariants. I didn't know much about it, but it seems quite an interesting topic. So these are some preliminary theorems or results concerning say join of two things, which is reflection and say cardinal invariance. So I should start by saying what is a reflection principle. I pretty much understand the same by reflection principle as compactness principle. It's any of the wide variety of principles which can consistently hold at a successor cardinal, while the successor cardinal is typically an inaccessible cardinal or large cardinal in some inner model. So you will lose some properties because you will use strong limitness, but you may retain some other properties. Classical examples are the tree property, stationary reflection, the failure of the approachability property, and possibly there are many others. We will discuss the interaction between these principles at the double successor of kappa and the higher cardinal invariance at kappa, and in particular the ultrafilter number at kappa. You know that the U of kappa is the size of the least size of a base of a uniform ultrafilter. To prevent any misunderstanding, if kappa is uncountable, the ultrafilter is required just to be uniform. It doesn't have to be complete in any way, just uniform. Okay, and we will focus on the case when kappa is a strong limit singular cardinal. This is a bit general. Usually the higher cardinal invariants are considered for regular cardinals, but at least the ultrafilter number can be reasonably considered at single strong limit cardinals as well. And it's proved by an easy lemma by Shelach and Gatti that even for a singular kappa, the U of kappa is at least kappa. It's at least kappa plus, sorry. So it's non-trivial. Let us briefly review the definitions of some of the compactness principles. So the tree property basically says that the infinitary logic at mu is compact without considering mu as an inaccessible cardinal. Stationary reflection, it just says that if you take a stationary set, it will reflect at some point. This is just, both of them are actually some compactness principles in first order. The first one in an infinitary version of logic, and regarding the stationarity, you can think of it as some kind of a compactness for the Levenheim-Skolem arguments. Regarding the non-approachability, I will just say that it implies the failure of the weak square, and in particular implies that there are no special Ahrenstein trees. Okay, so that's it. In the talk, I will talk about the tree property just because it's the hardest to obtain from these three. It's much easier to obtain stationary reflection, and it's easier to obtain the negation of AP than the full tree property. Okay, so there is an easy observation which is due already to Ahrenstein or Specker, that some reflection properties, in particular the tree property or the fact that you have no special Ahrenstein tree, implies the negation of GCH at kappa. So if we talk about, this may be a bit of an artificial question. I don't know if anyone studied it or not, but if you look at 2 to the kappa as a cardinal invariant, just C of kappa, then the reflection implies that C of kappa is higher than kappa plus plus. And the obvious question, and I said perhaps artificial, is whether actually any other cardinal invariants are pushed up. You may get some understanding of this fact. I mean, if you have 2 to the kappa is kappa plus, then you will construct a special Ahrenstein tree. But if you add a lot of Cohen reals, you will, for instance, Suslin trees are not destroyed by adding Cohen reals. So you can have special Ahrenstein trees with a large continuum. So it's not equivalent. You can have many trees, special Ahrenstein trees or Suslin trees without actually having small continuum. So one may ask whether there are any cardinal invariants which can be pushed up, which are in fact pushed up by reflection at kappa plus plus. Regarding the continuum function, which I think is the simplest Becker and Aroncha, in fact, it follows that 2 to the kappa is larger than kappa plus plus, and you may wonder whether this is the only restriction which you get from reflection, and probably it is the only reflection, you would say, and you would be correct. It's possible to consider an Easton-like theorem for these principles and take any continuum function which does not conflict with 2 to the kappa being larger than kappa plus plus, and you can realize it with the reflection properties you want. It takes some forcing argument. It's not difficult conceptually, but it's difficult because there is a lot of going on. There are many forcings and you need to control what's going on, but other than that, it's not too difficult, well, by present standards, because the results are already known. One can also show that the tree property at the double successor of a singular cardinal also does not restrict the value of the continuum function at Aleph omega. It implies the failure of a CH, but it does not tell you that it needs to be some minimal failure. You can get any finite gap you want. You may ask whether you can get an infinite gap. Possibly, yes, but the obstacles to the proof, there are some technical obstacles to make it work. But one would expect that you can have the tree property at Aleph plus 2 and infinite gap at Aleph omega. So, regarding this question whether reflection implies something non-trivial about cardinal invariants other than continuum function, so let us look at omega. There are many canonical forcings which will force the stationary reflection, tree property, and whatever you want. And you may start by looking at the models they yield and check what are the cardinal invariants. So you can get a model where essentially all the invariants are small. This is when you iterate the Sachs forcing for alpha too many steps. Everything is down regarding the cardinal invariants, but you have the tree property by an argument by Calamore from the 80s. If you want to have large cardinal invariants, you can just start with MM, and it will imply many of the reflection properties, and all the cardinal invariants are up. But in both of these situations, you actually have that 2 to the omega is omega 2. So this leaves open, for instance, the following questions. Suppose you have kappa is omega, but 2 to the omega is larger than omega 2. This is a common problem in this area because it's harder to have a gap larger than 2 at omega because you cannot use iterations of the proper forcings which add new reals. Or you may consider an uncountable kappa and talk about the reflection at kappa plus plus. I will focus on the second bullet. And I should say that the situation for uncountable kappa is less understood also because the properties of the forcings there are less understood. For instance, if you look at the kappa Sachs forcing, we just force with perfect trees of size kappa, you need to assume that there is some continuous splitting. I don't know if you've seen the definition, it's due to Calamore, I guess. And for instance, it's not clear whether under any assumptions actually the iteration of the kappa Sachs forcing will force small u. This is true for omega, and one would expect that perhaps this is true also for, say, a measurable kappa at least, because selective ultrafilter on omega translates into a normal ultrafilter at uncountable kappa. But actually the construction is inductive and it doesn't go through. I mean, the argument by Baumgartner and perhaps some other guy. Sorry? Yeah, Baumgartner and Lever. If you go through the construction, it just fails even for a measurable kappa. The bottom line is actually that it's consistent that you will destroy measurability by adding a single subset of kappa. So you cannot just hope that the construction will go through, because that would mean that over any model, Sachs forcing will preserve measurability. I should say if you are familiar with the proof for the Sachs forcing, the filter which is obtained in the end, if you use automatically what they do, is kappa complete. Okay, so if you extend it into a kappa complete ultrafilter, then you have measurability. So we study some results concerning the second bullet. So first theorem is with Vera-Fischer and Sharka-Stejskalova. So suppose you have two supercompact cardinals. I should say that this letter is upsilon, and I use it because Shelach and Garty use it. It's not very pleasant to look at. but okay, so kappa is less than even pronounced, it's not very, okay, so kappa is less than epsilon, there are supercompact kernels. Then there is a generic extension in which kappa is inaccessible, in fact probably supercompact, really large, 3 property holds in kappa plus plus, and you have a small ultrafilter number. Another theorem, this is Vicharka. Actually, you can obtain the same configuration with kappa being singular limit. And again, there is this assumption for 2 supercompact kernels. So we will discuss the second theorem. For simplicity, we consider the case of the minimal gap 2 to the kappa is kappa plus plus. So we will obtain an ultrafilter with character kappa plus, and 2 to the kappa will be kappa plus plus.
Can you get models where u kappa is small and u to the other models? Doesn't this kind of models that you consider?
I don't see any reason why the 3 property should hold there. I mean, in particular, in these models where this is obtained without the 3 property, the kappa plus plus was not a large kernel in a model, and to have the 3 property there, it's actually inaccessible in some model, in a model. I don't see any reason why the 3 property should hold in the models of Garty and Chelach, because you do nothing to get it there. But. Okay, so this is perhaps also interesting from the general forcing theory way, meaning that how hard is it to force the 3 property or any kind of reflection. And it seems that actually the forcing device by Mitchell, I should say that omega, for instance, Sachs forcing will force the 3 property, Grigoriev forcing will force the 3 property, even countable iteration of Cohen forcing will force the 3 property, and the Mitchell forcing will also force the 3 property. You always need some kind of ingredients, like some mixture of almost kappa plus closure and some strong form of kappa plus CC to make it work. But other than that, it's quite a robust construction. So let me consider some kind of a very generalized way to Mitchell forcing. So you have some forcing P, which is designed to do what you want. For instance, to force a small ultrafilter number, or anything you can wish for. What we only require is that it's an iteration of length delta, where delta, imagine, is something above a weakly compact or large kernel above kappa. The iteration has a strong form of kappa plus CC. This is pretty vague, actually. What is required is that actually the whole forcing, the square of it, and also the quotients have square CC. You know that to iterate, there is nothing like a uncountable support theorem for CC forcings, chain condition forcings. So actually, if you look into literature and people prove that some kind of iteration at uncountable kappa has nice chain condition, they usually require that the forcings have more than just kappa plus CC. They usually have some kind of linkedness or something which iterates. So this stronger form of kappa plus CC, which is actually very often a necessary assumption for the argument to show that you don't collapse kernels. Assume also that each Q alpha as a fresh subset of kappa. And think of P as a forcing which achieves the desired pattern of higher cardinal invariance. For instance, it may force a small ultrafilter number. In this talk, I will ignore what kind of arithmetics we need to make the computation right. Okay, so this is some kind of it's not very clear, the P inside of the picture, but sometimes it's useful to have some picture in your head. So think of kappa being a large cardinal. Usually, it's actually not necessary for kappa to be large. Very often, just regular is enough. But for the small ultrafilter number, kappa needs to be large, at least for the present method. It's open whether actually you need any kind of large cardinal stress for this, at least to my knowledge. Epsilon is a large cardinal, which has the desired reflection properties you wish for, and delta has the required cofinality, in our case, kappa plus. What you can do is to Mitchellize, in some sense, the P, in the sense that you will add a collapsing component, which will turn epsilon to kappa plus plus,
and collapse exactly the cardinals between kappa plus, open interval, and epsilon, open interval. And you do it by, sometimes this is called a mixed support iteration, that the support of P is typically less than kappa size. The support of the collapsing part is kappa size. And whenever you push up 2 to the kappa above kappa plus, at the next stage you will collapse 2 to the kappa to kappa plus. So once, if the P increases 2 to the kappa, then by forcing with cohen at kappa plus, you will collapse. Because this is known that, for instance, cohen at omega 1 forces that 2 to the omega is omega 1. So if you cohen there, you will collapse. There is actually nothing special about the cohen at kappa plus 1, which is the cohen forcing at kappa plus. You can use any kind of collapse you want, but it's not clear whether it's useful for anything. Okay. There is one more tweak to the usual Mitchell argument. The collapsing doesn't need to be defined everywhere. Think of the domain of the collapsing as being sufficiently sparse so that it has good gaps. I mean, I will show in a moment why it's good to have reasonable gaps in the definition of the domain of the collapse. So whenever you have such a P, you can consider P star, and what it should do by design is to collapse all between kappa plus and epsilon and force reflection properties at epsilon. I mean, force, they are there because it was a large cardinal, but it should be possible to show that they are preserved after it's collapsed. This is just, it was a picture which is helpful, but for those who want to see the exact definition. So suppose P is the iteration, and also note that the collapses are limited only, they go only up to epsilon. So for instance, if the delta is much larger than epsilon plus or anything, you can blow up the 2 to the kappa to be arbitrarily large, but the collapses only go up to epsilon. Okay, so A is the domain of the collapsing function. All it's required that it's cofinal. And the conditions are pairs P and Q. P is the first, is the condition from P. Q is the collapse. And the ordering is, as it's written there, you extend the P coordinate, and at alpha in the domain of Q, you extend the collapse. It's not a very pleasant forcing if you look at it first, because it's, as I said, it's a mixed support iteration. But I believe that Abraham analyzed this forcing very carefully in the 80s when he wrote a paper on the tree property at LF2 and LF3, because the original account by Mitchell is not very clearly written. So how do you proceed to actually analyze this forcing? It's usually done what's called the product analysis or projection from product analysis, in the sense that the forcing P star, which is the Mitchellized P, is equivalent to P star some quotient. And not only that, it's actually, there is a projection from the P cross T, where P is the original forcing and T is some term forcing, which is actually kappa plus closed. And then there is a projection from this product to your forcing P star. So in particular, because the product doesn't collapse kappa plus, neither does the P star. And what is good for us is that actually, because of the product analysis, you see that T is kappa plus closed. So actually all subsets of kappa or ordered sequences of length kappa are added just by P. So actually the quotient doesn't add new sequences of length kappa, so it's kappa plus distributive. So it follows that many properties of the cardinal invariants at kappa obtained in VP are actually preserved in VP star, because you do not add new subsets of kappa. So typically, for instance, for us, if you have a filter, ultrafilter with small base, then if you are not adding new subsets of kappa, the same ultrafilter will witness for the small u. Okay. There is something that you may ask, that it may still add some more complicated objects, like new ultrafilters with a small base or something like that. But in this simplified case, for the purposes of this talk, u of kappa is kappa plus. It cannot be any smaller. no matter what. So it's just enough to argue that the ultrafilter witnessing for small character in VP is still a witness for the character in VP star. So this was the Mitchell forcing with respect to a more complicated forcing than just the original Cohen forcing. And for the purposes of this talk, we will also plug in the end the Pre-Cree forcing. For simplicity, I use Pre-Cree forcing, but it can be Magidor forcing or radiant forcing, so any kind of forcing which singularizes kappa, kappa. So for these purposes, kappa needs to be a large cardinal, because in the end, we need to force with the Pre-Cree force. Upsilon is a large cardinal, again with the desired reflection properties. Delta has the required cofinality, and A is the domain. Okay. I should say something about the examples of P which appear in literature. If you look at this picture, and this P, this orange forcing, is just the plain Cohen forcing at kappa, then you will get the original Mitchell forcing. The first theorem I mentioned is that you can get a regular cardinal, actually inaccessible, with 2 to the kappa arbitrarily large and small ultrafilter number. Or you can get it with some work if you plug the following P's into the P star construction, in the sense that you will look at either of the 2 forcings which are available. They're actually, the second one is the simplified version of the first one, which in addition controls some other cardinal invariants. I will not go into details of this construction. And regarding the forcing for today's talk, or for the second theorem, there are nice papers by Gartier and Chelach from 2012. The first one seemingly doesn't have any connection to the ultrafilter number, but actually the forcing there is the one which is used in the second paper. So these are the forcings. I will briefly review it, but these are just references in case you would be interested in reading about these papers. So this is the P which is used in our theorem 2. So let me repeat the theorem. So we have 2 large cardinals, and you want to have a small U number, singularize kappa and blow up to the kappa to be large, and have any kind of reflection you want in kappa plus plus. And this is for simplicity what's been done. So review of this particular P by Gartier and Chelach. So what is done that to construct a small ultrafilter with a small character, they use some kind of PCF style like argument. So they first force a model where certain products at kappa, which is still regular, have true cofinality which is small, which is kappa plus, even though the 2 to the kappa can be very large. So this iteration looks like this. It's an iteration of length delta, which is cofinality kappa plus, and at each stage you will add a dominating function to a product indexed by some sequence from Gram model. Actually, in all these papers, you only need 2 sequences to consider, so you don't need to book, keep, or guess. Actually, 2 sequences are enough. Okay, so what are the properties of the forcing? It's kappa 2 linked. It's kind of a stronger form of kappa CC, kappa plus CC, which iterates. It's not even, it's only kappa, less than kappa strategically complete, which just means that not all sequences have lower bounds, only those where the second player chooses the right condition. So first player plays a condition, second one plays something, and the first player chooses a condition below these 2, so that at limit stages it can continue. So it's not closed, but providing that you have the strategy, you can do pretty much the closure arguments you are used to. With a modification of the labor argument, we can be prepared so that we preserve supercompactness of kappa. I should say that you are all familiar with the labor preparation. It's formulated for kappa-directed close forcings, and it's known that it doesn't hold in general for just kappa close forcings. But if you go into the details of the proof, you will see that very often you can do with much less, because a directed family to which, for those who just know something about it, The point is that you want to argue that a pointwise image of a generic has a lower bound. And the pointwise image of a generic under some elementary embedding is smaller than directed. For instance, if the forcing has lower bounds or greatest lower bounds for sequences of certain length, then actually you cannot fall out of the pointwise image of the generic. So you can actually show Lever-like theorem for more than just kappa-directed closed forcings. Okay, so let me see. Okay, so in VP, you will have sequence of measurable cardinals of length kappa converging to kappa where the GCH holds. Recall that 2 to the kappa is arbitrarily large, so you need to choose some sequence of measurable cardinals which is not in a normal measure. And you have the true cofinalities of the product with respect to the bounded ideal or ideal of bounded subsets of kappa, and the sequence of the successes of those measurable cardinals has true cofinality kappa plus. This kappa plus is the cofinality of delta. If you want to have another true cofinality, we choose your delta with different cofinality. And this is just for those who want to look at the result. I believe that the result is interesting by itself, and I do not know whether people worked on it or not. You just, over this model where kappa is regular, 2 to the kappa is arbitrarily large, you have these two products have nice true cofinality, and then there is a combinatorial lemma which says that if you force with a Precri forcing, actually the products will have still the true cofinality if you index them only by the members of the Precri sequence. Okay, so, and this is used in the other paper to actually build by hand a ultrafilter with small character. One more regarding this paper. They formulated only for simple Precri forcing, so you get cofinality omega. They mention in passing in one sentence that the same proof will go through for Magidor forcing for uncountable cofinalities. I should say that perhaps this is the case. If you go to the details of these papers, they are very similar to a related result. At least I hope it's related. This is by Magidor and Chelak, that if you have a singular limit of strongly compact cardinals, you have the tree property at a successor. And the proof actually does not depend on the limit having countable cofinality. It goes through for any kind of, providing it's singular, the proof will go through. So possibly this is very much similar construction, that because in the second paper, which has the letter B there, this is just a combinatorial argument. It's no forcing argument. Just say, suppose you have these true cofinalities, suppose you have these enumerations of certain sets, then you will construct an ultrafilter with small character. And they do not require that actually the singular cardinal has countable cofinality. Another point, I will mention it in the open question section. You might wonder whether actually you can collapse kappa to be, for instance, Aleph omega. Very often this can be done. For instance, Magidor collapsed, had omega many strongly compact cardinals, and at their successor you have the tree property, and he collapsed all of them to be Aleph omega, and the tree property was preserved. So we might hope that something like that might perhaps go here as well, although it will be a complicated construction because the combinatorial argument requires that kappa is a singular limit of measurable cardinals. So you cannot just hope that you will plug in the Precri with collapses and then just use the combinatorial lemma of Cartier and Chelak, because it requires it's a limit of measurable cardinals, so it cannot be Aleph omega or anything small actually. So we need to somehow combine collapsing and the combinatorial argument. Okay. So in order to prove the theorem 2, consider the following forcing. We'll Mitchellize this forcing, making the true cofinality small, and you plug in the Precri forcing after that. Notice, for instance, that kappa is measurable in P because of the Lever preparation, and P star, the quotient doesn't add new subsets of kappa, so it's still measurable. So you can actually, this is well defined, P star Precri is a legitimate definition. So we need to show two things, that the ultrafilter number is still small, small, and that you do have a reflection of the type you want at the epsilon, which is the nu kappa plus plus. I will not spend too much time on nu kappa. It's rather tedious verification that you will not undo by your quotient what is done by p, and you need to check the technical lemmas and the combinatorics. But actually you are not changing the product because you are not adding new sequences of length kappa reserve, etc. So let us focus on the tree property argument. As I said, epsilon was a large cardinal. For the purposes of this talk, it could be just weakly compact. I will say something in the end about why we require that epsilon is actually super compact. It doesn't seem to be optimal, but I will get into it. Okay, so suppose you have an elementary embedding with critical point epsilon. The restriction of that embedding to R is a regular embedding, so you can take a quotient of the K image of the forcing by your original forcing. And the strategy now is pretty much standard. You will argue that any epsilon 3 in M of R, and let me fast forward for this picture. The orange part is still the P part, which does the non-trivial thing regarding the U number, and the yellow part is the collapsing. And you take the K image of this forcing, and it looks like this. Okay, you notice that the yellow part on the left-hand side should actually extend all the way on the other side, but I said that actually the collapsing is defined on some relatively sparse set. So you can make it so that the K image of the domain of the collapsing actually avoids the interval epsilon and delta. So if you look at it, the quotient Q is actually the tail iteration of the K image of R, actually is equivalent to it. And if you want to show that the tree property or stationary reflection is preserved, you follow the usual trail. We'll just say that if there was an epsilon Aronsheim tree in M of R, I didn't write it, but the left-hand side is V, the right-hand side is M. So if there was an Aronsheim tree at epsilon in the model where you have just the iteration below delta, then, and you know that there is actually a cofinal branch in that tree in the whole extension M of K of R. So all it suffices to show that the quotient cannot add a branch to epsilon trees. Because if you look at this picture, notice that this is without the pre-Cre collapse, and the P star is not the usual Cohen forcing, so it's some kind of a more complicated non-homogeneous iteration. But still you can show that because of this representation of this gap between epsilon and delta, that it decomposes into a product, meaning you can regularly embed the tail iteration into a product of nicely chained condition forcing and nice closure forcing. Okay, so this is just what it says. The quotient, technically speaking, is what's written there. There are all conditions in the K image of the iteration which are compatible with every condition in the pointwise image of the generic. But luckily for us, luckily by design, it's actually equivalent to the tail iteration, which can be easily analyzed. So this is the usual standard projection from product analysis. I will lead you to Abraham in the 80s. I should say that in VP, it's not clear whether you have a small U number. All the lemmas in papers by Shellac and Garty use the assumption that kappa is singular, and kappa is still regular in this model. But actually, so far as we looked, we couldn't actually find a place where they use that kappa is singular. So, but probably they do, one could say. Okay, so, but, well, as I wrote, it's not ensured that you have a small ultrafilter number in this particular model. Okay, so, but you can show by the quotient analysis that you do have the tree property in this VP star. Now, suppose you plug in the pre-Cre forcing after that. Now the quotient analysis gets pretty nasty in the sense that it's no longer an iteration. You have an iteration, then you have a single forcing. Now, if you look at the K image of it, you still want to decompose the forcing so that it starts as the forcing on the left and then continues somehow. But it's not a tail iteration. It cannot be because you already added a pre-Cri sequence. Now, using the geometric criterion, the sequence which works for the pre-Cri at the top is actually the one which works in the middle. So actually what it looks like is the footnote 8. This tail iteration or whatever, this quotient iteration, quotient forcing, you can imagine it as a tail of the P iteration which somehow must avoid all the dense subsets which would cause collapsing kappa to omega. Because put in the pre-Cri generic on the right hand side, a delta, kappa gets singular, it just has cofinality omega. So if you add a single coherent real without making sure that it doesn't make damage, it would collapse everything to omega. So it's some kind of a strange quotient which adds a lot of new subsets of kappa, but all of them avoid just the right dense sets. Technically speaking, again, it's just all conditions in K P star star pre-Cri. I should know that by elementarity, the whole forcing on the right hand side looks like a longer version of P star and then the pre-Cri forcing after it. And you need to respect the pointwise image of the generic. So it cannot be, we actually try to analyze it by the projection to product approach, but it doesn't seem to work. So we actually, when it goes back to a technique introduced by Tsai and Halilovic, I will refer to that paper after a couple of slides. So you need to argue more. There is no nice argument which will just says because you have a projection from nice chain condition and nice closure forcing, you have the tree property. You actually need to compute that you have the tree property and essentially do it by analyzing the forcing, the first pre-Cri star the quotient, which is this unpleasant iteration which ends with the pre-Cri. And you try to make sure that if there was an Arnstein tree and a new branch, that you might construct some kind of a perfect tree of conditions which decide more and more about the branch you assume exists by contradiction, and in the end you will find a contradiction inside of your tree. I will not go into details, but I'll just say that you still need some kind of strong form of CC for the quotient of P after P. Some kind of a iteration, and you take the quotient after the iteration. So you need to do some work to compute that it still has kappa plus CC. Let me just say, what are the problems with this analysis? The quotient is very unpleasant in the sense that if you have, I should also say, you might wonder why you don't work just with the Q, which is the quotient, but you work with a more complicated forcing, the pre-Cri star Q. The point is that after the pre-Cri, kappa is singular, and you cannot do any kind of inductive construction longer than omega, because you would just fall out of the forcing. So you need to work over a model where actually you do have a chance of longer construction. So this is before the pre-Cri. So the argument always talks about when a pre-Cri condition forces some other condition to be in the quotient. And it's unpleasant in the sense that you have a very simple condition which forces a condition in the quotient, in the K image of the forcing into the quotient, another one into the quotient, in the K this lower bound, but the same condition actually forces that lower bound outside of the quotient. So it's kind of an unpleasant situation, and we solved it using the fact that the pre-Cri condition in the first pre-Cri and the condition in the second pre-Cri, which is hidden in Q, you see that the conditions in Q are actually just members of P star pre-Cri and K image of it. So you have a Berkeley hidden in Q that they have the stem decided. Okay. Now, as I said, this idea for the construction of the tree of conditions goes back to an early argument for Friedman and Halilovic, which they proved the tree property at the double successor of Aleph omega. And this was for the Sykes forcing, which actually made the construction much more complicated. So if you use the Mitchell forcing, it's actually more streamlined and it's easier to understand what's going on. And I should say that unlike the Mitchell forcing, where P is an homogeneous Cohen forcing, some of these things are complicated with our genuine iteration. Before I get to the open questions, I should say that those who know these types of results might wonder why is upsilon super compact and not just weakly compact, because tree property doesn't require more than weak compactness. The reasons are quite actually straightforward. The point is that if you look at this picture, actually even this one, you can see that the embedding K non-trivially, I mean the iteration P is of length delta, so it's actually past the critical point. So you know that when you are lifting an embedding, you need to have it, the lifted generic needs to contain the pointwise image of the generic on the left-hand side. Now this is very easy if actually the epsilon, but it goes to delta, so it non-trivially moves the conditions, and it's not a product, it's an iteration, and just disperses it somewhere up. And now, how do you actually do this quotient analysis? You actually need to argue that this K restricted to a forcing is a member of M, so that actually you can get the generic on the left-hand side to be a member of the model on the right-hand side. Some kind of a technical detail, but the only way how we can ensure that for the moment is that we actually assume that the K image of that forcing is a member of M. And in general, if we want to have an arbitrary gap, this just means that you need to have a closure on the arbitrary long sequences, which is a supercompactness. It seems like very awkward way to handle things, but perhaps not. I mean, if you have just the Cohen forcing there, you do some kind of automorphism argument. If a tree was added by some segment of the Cohen forcing, it would be a small segment because of the chain condition. You can take an automorphism to a smaller part of the Cohen forcing, and that's it. But the P now is a very unpleasant iteration, so you cannot just say that a chunk of it is, you can take an automorphism to some small part. Okay. So this is the supercompactness part. Let us go. I said that the theorems are formulated for cofinality omega, but the technical papers of Garty and Chelach claim, without giving details, that you can do it for Magidor forcing or the radial forcing. So one might check first whether what they claim in passing is actually true, which to my knowledge has not been verified, and it's known that they may be pitfalls, I mean, unless you check it for details. Okay, so one thing is that it's not clear whether you can do it for uncountable cofinalities, but probably yes. Second question is, can you actually bring the construction, and now I talk even just about the small u number, can you bring it down to a small cardinal, something like Aleph omega or Aleph omega squared? Let me just say something. I still have 2 minutes or so. Yeah. I mentioned the result by Magidor and Chelach, where they obtained the tree property at Aleph omega plus 1 by collapsing omega many supercompact, strongly compact cardinals. In their model, you have GCH at Aleph omega. So at least you cannot have the tree property at the double successor, because this violates GCH at Aleph omega. So if you would like to have a small ultrafilter number at Aleph omega plus reflection at Aleph omega plus 2, you would need to look probably to some kind of a version of a diagonal supercompact Berkeley forcing, because there is a paper by Dima and Spencer on having tree property at Aleph omega plus 1 and Aleph omega square plus 1 and Aleph omega square plus 2. So they have a value of GCH there. So perhaps by these methods you might hope to answer the second bullet. And this is completely notorious question probably, whether you can have a small u kappa for a successor kappa. I do not know of any such model. What is the consistency strength of u of kappa being smaller than 2 to the kappa for kappa uncountable? Recall that if for kappa omega, the consistency strength is just ZFC, in the sense that if you have selective ultrafilters, you have a small u number, and you can force the situation without assuming any large cardinals. So the consistency strength for kappa is just ZFC if kappa is omega. But I do not know otherwise. All the methods which are known in the literature use that kappa is super compact. Perhaps for the lame reason, in quotes, that you recall, that you will refer to the labor preparation. But perhaps there are deeper reasons behind it. I don't know. And this is just about the cardinal invariant. I mentioned that if you want to keep kappa regular, there is a paper by Sai, Diana, Vera, and perhaps Andrew. And what they did actually, that they have a more complicated P, so that at even coordinates it controls the u number, and at odd coordinates you can do anything you want. If you plug it into this construction, it will work just the same. So you can control more than just u number. You can control more cardinal invariants, and you can think about some Easton-like theorem. Regarding these Easton-like theorems, it's always been embarrassing for perhaps for set theorists with respect to mathematics, is that ZFC proves very little about the continuum function. So there may be a tendency to actually, if you want more from the continuum function, for instance, to preserve large cardinals or to preserve reflection or something like that, then perhaps ZFC can prove more restrictions than just these two conditions like Koenig's lemma and monotonicity. So there are Easton-like theorems for large cardinals. You may think about Easton-like theorems for cardinal invariants, which is actually a paper by James and Chelach from the 80s when you control B kappa and D kappa. I believe Vera recently talked about controlling S kappa or something like that. So, and you can think about combinations of these if you wish, at least for some reasons. Okay, so these are the references of the papers, and thank you for your attention.